Assalamu alaikum everyone, it's Mr. Fahad. Today we will continue with the fifth lesson. This is the first part, limits involving infinity. We will be focusing on asymptotes. By the end of the lesson, you should be able to find infinite limits, meaning the limit's value is infinity, and limits at infinity, meaning when x is approaching infinity. Okay, so let's start with the main concept, asymptotes. In this graph for the function 1 over x, we have vertical and horizontal asymptotes. So with the horizontal asymptote, as values of x increasing, the value for f of x is approaching to 0. So you can think of 1 over 100, which is near 0, 1 over 1,000, 1 over million. So as we approach extremely larger values of x, the f of x or the y is converging to 0, but never quite reach 0. So we call this an asymptote. And similarly here, we have a vertical asymptote where values of x approaching 0, the y values will be approaching infinity or negative infinity. All right, so let's study this function to learn more. So with this function, it's a rational expression. You can first factor it out and try to simplify the expression. You can see zeros of the denominator at x equals 1 and x equals negative 2. So these two values makes the denominator 0, which makes the function undefined. Okay, so let's study the behavior of the function at these points. At x equals 1, x equals negative 2, and we will add x equals negative 3. So at x equals 1, the function is undefined, and the limit exists. You can substitute 1 in the simplified expression. You can see if we substituted 1 in the simplified function, this will be 4 over 3. So the limit exists, but the function is undefined. This means we have a removable discontinuity, a hole in the graph. At x equals negative 2, it's a 0 of the denominator, and you can see the numerator will still have a value. So this will be a vertical asymptote. It's non-removable discontinuity, all right? With the third point, we have the numerator equals 0, but the denominator is not, and this is a 0 of the function. So if we graph the function, I can see at x equals 1, there's a hole in the graph. At x equals negative 2, there's a vertical asymptote, and at negative 3, we have an intersect with the x-axis. So it's important that you distinguish between the removable discontinuity, when you have a hole, and with the vertical asymptote. So whenever the factor is cancelled, this means at this 0, you have a hole. But with the vertical asymptote, the factor will never be cancelled. So you will see the 0 in the simplified function. Okay. Let's take another example. Evaluate limit when x approaches 0 for 1 over x squared. So I can see that at 0, the function will be undefined. This means we have a vertical asymptote at this point. Now, to evaluate the limit, we will use the numerical approach where we substitute values of x in the function. And you can see as x approach 0 from the right, the values will be approaching infinity. And from the left is also approaching infinity. So I can see now that the limit at this vertical asymptote is approaching infinity. And you can verify this also graphically. Looking at the graph, you can see how the vertical asymptote at 0 and the function is approaching infinity on the both sides of the vertical asymptote. Let's study another example. Find the limit when x approach 5 for this function. The easiest way to solve this is using your calculator, where we use the numerical approximation method. So just write the expression and then hit on calculate. From the right side, you have 5 zeros and then 1. And this equals an extremely large number, so infinity. And then calculate. And now from the left side, 4.9s. And this is approaching extremely negative large number. So negative infinity. So therefore, I can tell that the limit does not exist. Now, if you want to do this without using your calculator, whenever the denominator trends to 0 and the numerator is not, we determine whether the limit trends to infinity or negative infinity by examining the sign of various factors. So imagine here if you have the limit around 5, and you will substitute a number larger than 5. So the limit when x approached to 5 from the right side, you have on the top a positive value, and down here you have larger than 5, minus 5, so a positive value, and therefore the limit from the right side will approach infinity. Now from the left side, when you substitute value less than 5 minus 5, so this will be negative, and therefore it's approaching negative infinity from the left side. Now I can tell that the limit does not exist, and you can verify this graphically. Looking at the graph, you can see that the limit does not exist. All right, next we have the limit when x approach pi over 2 for tan of x. Now pause the video and try to solve this using your calculator. Remember, set your calculator to radians. So using your calculator, substituting pi over 2, you can see it's not defined. So you will try to approach from the right, from the left. You can do this by taking 0.501 times pi. This is from the right side. And I can see it approach large number, negative number, so negative infinity. Calculate from the left side 0.49 times pi, and this equals a large positive number, so positive infinity. Therefore, I can say that the limit does not exist. Now let's solve it without using our calculator. So since it's not defined at pi over 2, we will try to factor out the expression sine of x over cosine of x. This will help us evaluate it also. So let's take the expression from the right side. When the angle is larger than pi over 2, I know that the sine will be positive, but the cosine in the second quadrant is negative. Therefore, it approaches negative infinity. Now, if it's less than pi over 2, so first quadrant, both are positive, and therefore positive infinity. So I can say that the limit does not exist. And you can verify this looking at the graph. Here's the asymptote and the limit on the right side. On the left side, you can see they are approaching different infinities. Now, in this example, we've been asked to determine all vertical asymptotes. And for each vertical asymptote, at each point, we need to find the limit from the right and from the left side and decide whether the function is going to infinity or negative infinity. With the first function, first we need to look at the zeros of the denominator. So set 1 minus x squared to 0 and then factor it out. This will gives us the points where the function has a vertical asymptote. Remember, at these points, the function is not defined. Now, in order to evaluate the limit around it, we can simply use our calculator. For this question, I recommend that you just use the numerical approach method, and that's it. All right, so using our calculator, we will try to evaluate around -1. So from the left side, it will be -1.01, and this is infinity. Again, it's either infinity or negative infinity. So if it's a large number, this means infinity. Now let's look at the other side, from the right side, and this equals negative infinity. So I know at -1 from the right side, it goes to negative infinity, left side infinity. Now we will do the same at 1. So from the left side, 0.9s, and this will be infinity. And now at the right side, at 1, 0, 1, this will be negative infinity. So you can see from the right side, you can verify your answer looking at the graph. Now, without using your calculator, just like we did with the previous example, try to evaluate the expression. And of course, the limit does not exist at both points. All right? Here's a question for you. Determine all vertical asymptotes for each point. Find the limit around the vertical asymptote. So you need to tell whether it goes to infinity or negative infinity. Please pause the video, try to do this, and then come back to check your answer. Okay, let's solve the question. So the first thing, to find vertical asymptotes, we need to factor out the denominator and set it to 0. All right, so from here I can see at x equals 0 and at x equals 2. But since this factor is shared, at x equals 2, we will get a hole in the graph. And the vertical asymptote will be at x equals 0. Now, in order to evaluate the limit around the vertical asymptote, we will use our calculator to approach 0 from the negative side, the left side. And this will be approaching negative infinity from the right side. So calculate 0.01, and this equals infinity. Now you can solve this without using your calculator by evaluating the values, and you can see that the limit does not exist. At 2, we have a removable discontinuity, a hole, and at 0, we have a vertical asymptote. That's it. Moving next, in this question, we need to determine the vertical asymptote for this function. Since this is a len function, just like the log functions, it's only defined for the positive values. So what's inside should be positive. So set what's inside to an inequality. It should be larger than 0, and therefore x is larger than 2. And now I know that there's a one-side vertical asymptote because the function is not defined for the values less than 2. So looking at the values to the right of 2, you can take the limit when x approaching 2 from the right side and evaluate it using your calculator. So using our calculator, substituting at a value larger than 2, the function will be approaching negative value. Now, if we approach more, you can see that the value is approaching larger and larger. And looking at the graph, I can see it's approaching negative infinity. All right, so the last part for this video is the end behavior for the polynomial functions. Now, for polynomial of positive degree on this form, the limit of the polynomial when x is approaching infinity depends on the coefficient for the leading term. So the coefficient of the leading term, if it's positive, then it will approach positive infinity. If it's negative, the limit will approach negative infinity. But when you are looking at the limit when x is approaching negative infinity, then you have to consider the degree or the power of the leading term. If it's even, then the limit will approach infinity. But if it's odd, then the answer will get the negative sign. Let's practice on this with these questions. Evaluate the limit when x is approaching infinity for this polynomial function. Since we are approaching infinity, I will only look at the leading coefficient, which is positive number. Therefore, the limit will approach infinity. With the second question, x is approaching negative infinity, and I need to pay attention to the degree. Now, since it's odd and it's positive, this will approach negative infinity. Again, when x is approaching negative infinity and the power is odd, then the negative sign will show at the answer. All right, here's number of questions for you to practice. Please pause the video and try to solve the questions. All right, let's solve the question. So with the first limit, x is approaching infinity, I only need to pay attention to the coefficient. I can see it's a negative leading coefficient. This means it's approaching negative infinity. With the second one, and please pay attention, x is approaching negative infinity. Now, you need to pay attention to the degree. Since it's even, this will turn into a positive infinity. But then, since the coefficient is negative, this will turn again to negative infinity. So the answer will be negative infinity. And for the last question, x is approaching negative infinity. So you need to pay attention to the power. It's odd. So the negative sign will show at the end, but then you have the leading coefficient as negative times negative, which is a positive infinity. I hope this was useful. Thank you for watching. See you in the next part.